Hey, welcome to the video. This episode is not sponsored by Spindrift. All right, today we're going to be looking at solving a little algorithm from LeetCode. It's called find first and last position of element in sorted array. The problem statement goes, given an array of integers nums sorted in non-decreasing order, find the starting and ending position of a given target value. If target is not found in the array, return -1, -1. And then it also says, you must write an algorithm with O of log n runtime complexity. So let's look at a real quick example. So here is an array, and we'll go ahead and just put the indices up top. Now, let's say we're looking for the target number of 5. Well, in this case, the first index of 5 is 4, and the last index is 5. So in this case, we would return the result 4, 5. We're also told that if we're not able to find the target number in the array, we should just return -1, -1. So let's just really quickly look at an example of that. So everything in the array this time is the same, except at indices 4 and 5, I just replaced the elements with 6 and 7. We'll keep our target as 5, and this time, since we're not able to find 5 in the array, our return value is just -1, -1. All right, now that we have a good understanding of the actual problem statement, the first thing I'm going to do is whiteboard this out on my iPad and just kind of do a visualization of my approach to this problem. And then after we have a good understanding of the actual algorithm of how we can solve this problem with the desired time complexity, then we'll go and we'll write the actual code for it. But first things first, let's go do some whiteboarding. All right, so I'm just going to come up now with an example array we can use to try and solve this problem. So I'm just going to start arbitrarily throwing some numbers in this thing. All right, so this is our array, and I'm just going to go ahead now and just label the index of each element in the array, just so as I'm talking through it and thinking through things, I don't accidentally give the wrong indices for any of these. All right, so we're going to go through 3 different ways to try and solve this problem. And the first one we do is going to kind of be the easiest way, but also the least efficient. And then after that, we'll do one that is a little bit more complex, more efficient. And then finally, we'll do something that actually gets us the best case time complexity that we're going for, O of log n. And that will be our final solution. All right, so we are going to make use of a searching algorithm called linear search. This is going to be the most simple algorithm, and as the name suggests, what we're going to do is start at the first element in the array and then linearly move one element at a time until we find the number that we're looking through. So, for example, if we look at our array on the iPad, this dot here is going to be our starting point, and let's say up here we're going to say that the target number that we're looking for is 11. Okay, so we'll start at the first position. It's not 11, so that's not the one. We'll go to the next one. That's not the one. Go to the next one. Nope. And then the same thing. We're just going to hop through these guys one at a time, searching until we find 11. And now here we can see that at index 10, we finally found what we're looking for. So for just like the simple search approach of finding a number in an array, right? That's what linear search is. We did that. Now for this specific problem, again, we're not just finding the element the first time where it is, but we need to actually find it the first time and the last time, and we have to return those start and end indices. So for here, using linear search, we found that start indice of 10, and I'm going to go ahead, I'm going to just write our solution up here in gold, and so the first part of that is 11, but we haven't found the end index yet. And so using linear search still, we will continue. I'm going to switch colors, right? We were previously at index 10, and now what we're going to do is we're going to keep hopping until we find a number that is not 11, and that's how we know where the sequence of 11s ends. So we're going to go from 10 to 11 to index 12, and then at index 13, finally, we see that that is not an 11. It's not what we're looking for. So in our solution here, we can fill that in with a 13. All right, so now let's talk about the time complexity of this algorithm. Again, the goal is O of log n. So as you can see, just from looking at this example, we had to start at index 0 and then move one index at a time all the way until we got to index 10, meaning that we had to hop 10 hops. And then in order to find where the last index is, we had to take another 3 hops after that. So we actually ended up traversing every element in the array in order to find the solution. And so that gives us a time complexity of O of n, which is worse than our goal of O log of n. So now we're going to switch it up, go to a different algorithm, and see how that can improve our time complexity. All right, so this next algorithm, we're going to be using binary search. This is another searching algorithm that's very common for this exact type of solution where you're trying to find a number in a pre-sorted array. In this case, we will use binary search to find the number that we're looking for. And then at that point, we're going to have to move from that position to find where both the start and end indices are. So for example, when we're using binary search and we're looking for 11, say when we're looking at that example array, say that we ended up at index 11, well, we still have to figure out that there's actually the 11 at index 10, and we got to move forward to find the one at index 12. So from there, we're going to actually use the linear search again and just move one step at a time, backwards first to find the start index, and then forwards to find the end index. So in order to implement our binary search, what we're going to have is 2 different pointers that point at our positions in the array. We're going to call them L and R for left and right. And we're going to start the left one all the way at the beginning of the array. And then the right one will go at the end of the array. And then what we'll do is we'll find the midpoint between those. I hope you guys don't hear my dog barking. And then what we're going to do is we're going to find the midpoint halfway between those and look at the value inside that element. And if it's equal to the target value that we're looking for, then we found it, we can stop the binary search. However, if the value is less than what we're looking for, so the value in there is smaller, like so say we found 5 and we're looking for 11, what we're going to do is we're going to take that left pointer and move it to the position 1 after that midpoint we looked at. The right pointer will still be at the end, and so then we're basically going to repeat that process where we have our left and right. We're going to find the midpoint between them, look at the value in there, and let's say that this time the value is greater than what we're looking for, in which case now we'll take the right pointer, move it one position before that midpoint we just looked at, and we're going to just keep doing that repeatedly until either we can't look anymore or we found what we're looking for. So let's go ahead and now draw out a little diagram of this binary search algorithm. So as I said, we're going to have the pointer L going to position 0 and our R pointing at position 13. And now we'll calculate that midpoint, which is just going to be equal to L plus R divided by 2. So that's 0 plus 13 divided by 2, which is just going to be truncated to 6. And so M is pointing at that 9 at index 6. And so if we're looking for our target of 11, well, 9 is less than 11. So like I said, we're going to take our L pointer and we are going to move it one position past where we were looking before with that midpoint pointer. So now L is going to point to 7. So now I'm going to just take a subslice of that array with our new left and right, and we're just going to look at that and repeat the process. So let's copy starting at index 7. We have 9, and then another 9, a 10, and then 3 11s, and a 12. And then I'm going to copy down those indices from the original array so we don't actually make mistakes and forget where we are in the array. All right, and so L is pointing at index 7, R is pointing at index 12. Let's calculate our new midpoint. So M equals L plus R over 2, which equals 7 plus 13 over 2 equals 10. Is that right? I feel like I did something wrong, but yeah, no, I think that's right. So M now points at index 10, and that holds the value 11 we're looking for. So now we've actually finished that first phase of binary search, right? Our goal was to find a number 11, and we did it. So now we need to go to the next step, and that's going to be finding both the start and the end. In this case, we actually did end up at the start, so we don't need to look any further, but let's go ahead and explore how we can find where the last position is. And to do that, we're just going to use linear search. So the same thing that we had done before with like our initial approach that had the O of log n time complexity. So what I'm going to do is I'm going to copy starting at index 10, that point forward, and label all these indices. And so, right, we had already reached the conclusion that at index 10, we found our wonderful value of 11, which is what we were looking for. And so now we need to find our end index, and we're just going to do our linear search. So we're just going to hop to 11, and we see there's another 11 there. We hop to 12, we see there's one in there, and then, oh shoot. And then we hop to index 13, and we've got a 12. And since this is a sorted array, right, every number is going to be at greater than or equal to the previous one. We know that we found the last 11. And so now we've got our solution, which is just going to be starts at 10 and ends at 12. All right, now let's analyze our time complexity of this one. So using the binary search, right, we had this thing where we're starting from the beginning and the end of the array, and then we look in the middle. And then based on the result of that, basically we look in one of those halves and find the middle of that. And then we're going to look in one of the halves of that and keep dividing this thing in half until we find what we're looking for. And so in that way, you can see that actually like the search space of elements in the array we're looking for on every iteration decreases by a factor of 2. So every time we're having the search space. And so that's what gives us this O of log n time complexity when we're searching, when we're doing our initial search to find our target value, which in this case was 11. After that, we then went and we used linear search to go forward and find where the end index is. In our particular case, our initial round of binary search actually gave us the start index, but that's not necessarily always going to be the case, right? It could have ended up, let's say like on index 12 or index 11, and then there would have been one before and after. Pretty much anything could happen. And so if there were more 11s before, basically we would have done the same thing where we just traversed one at a time forward, but just do that going backwards until we've reached the last 11, and that would have given us our start index. And so the problem with that is, again, we're using linear search, and that is going to give us an O of n time complexity. Even though we were really efficient with how we found the first 11, the fact that we use linear search after that actually just kind of degraded the entire algorithm. And so to just kind of emphasize why that is the case, let me draw out a new array over here. So right before we had those 3 11s, but let's say right now our target is going to be 8. And let's say that our array is just nothing but 8s. Well, so with this, right, we're going to have, let me label our indices, 0, 1, 2, 3, 4, 5, 6, and 7. We've got L here, we got R here, M is going to be 0 plus 7 over 2 equals 3, which is going to be that. So that was like our initial round of binary search, and we ended up on index 3, and we found an 8. Wow, that was amazing. But now we're going to see like how we perform that step of finding the first and end index from there. So what we would do from there, I'm going to just take my gold out, right? We found this from binary search, and now we need to find the start. So we're going to hop backwards, and we're going to hop backwards, and then we hop backwards again, and then we found the start was at 0, and now we're going to hop forwards to find that end index. So we go to 4, 5, 6, 7, and then we reach the end of the array. So we found our start indices of 0 and 7. Now, if you look at that, we actually ended up going through every single element in the array. So that's why it's O of log n, right? The time complexity is equal to the size of the array, and that's not good. That's not the goal. Now we're going to look at a third approach, and this one will give us that O of log n time complexity that we're going for. All right, our third and final algorithm is going to start out identical to our previous one in that we're going to use binary search until we happen to hit the element that we're looking for, or we run out of search space. So to start it out, I'm actually just going to copy over the results we had from that, because again, it's going to be the same thing and there's no reason to repeat that. So we had our L was pointing at 7, our R was pointing at 13, and M was pointing at 10. And so in the previous algorithm, this is where we used linear search to keep moving forward until we found the end. And now what we're going to do instead is we're going to use binary search to find the end. Okay, so let's say, right, we hit this step, we've reached element 10, and now what we're going to do is we're actually going to take our left pointer and we're going to move it one position past our current midpoint, and now we're going to do binary search within here to find 11. So our new subslice is going to look like this. We're going to have 11, 11, and 12. And those are at indices 11. Actually, I'm going to do them on the bottom. I think I like that more. 11, 12, and 13. And so now we've got L pointing at this guy, R pointing at this guy. We don't even need to do the math. We know that M is pointing at that. And that gives us an 11. That's cool. But what we're actually trying to do is keep going until we don't hit an 11, because that's how we know it ended. So now what we're going to do, again, is we're going to take our left pointer, move them on over one past M, and now we'll take the next subslice, which in this case is just going to be the number 12, which is at index 13, and both L and R are going to point to 13. And right, pretty obviously our new M is just going to be 13, but we'll go ahead and do the L plus R. And that equals, that was really sloppy. And that equals 12, that equals 13. So it points to index 13, which has that value of 12. And now we've reached our stopping case, which is that we found all the 11s. And so if we look back at our previous one, we had our M of 12. And so we know now that our final solution is that start index that we had from before, which was at 10. And then our new end index, which was from the previous iteration, because that one actually found 11. We don't use the midpoint from this one because it wasn't 11, but it told us that we had reached the end. And from the previous one, we had this 12. And so this is our indices for the result. All right, now really quickly, let's go over the time complexity of this solution. So I'm going to go ahead and do kind of what I did last time, and that is just fill out an array with a bunch of 8s in it, and 8 is going to be our target, and we're going to see how using kind of this double binary search thing might help us. And then go ahead and just label all of these. Okay, so in this case, the first place we would have gone to was here. And then we're going to start out by, because in this case that we didn't actually have the start index happen to be the one that we found. And so what we would do after that is we would be looking at this subsection. And then what we would do, halfway point of that would have been, let me switch colors actually. The halfway point of that would have been here. We still found one, so we would have kept going. So now we'd actually be looking at this subsection, and our halfway point within there would be right here. And then we would just end up looking at this final one, at which case we would be at the beginning of the array, and that would give us our solution. So really quickly, just like intuition on that is, you can see that we went from 7. We didn't even have to look at, let me cross out all the ones we didn't have to look at. So we didn't have to look at 6. We didn't have to look at 5. We didn't look at 4. We didn't look at 2. But we did look at indices 7, 3, 1, and 0 in order to find the start. So we were able to skip some. And if you're dealing with like a much bigger array, that would actually become pretty useful. Now, similarly, to find the end index, right, we'd be looking at this subsection of the array. And this one I've got to actually do a little bit of math. So we're going to have 23 divided by 2 is going to be, I think, 11. I might screw up some stuff here, but it's mostly to make the point. So here we were at 11. We're going to keep going. What did I switch to last time? Purple. So now we're going to be looking at this section of it. And then our halfway between 12 and 17 would be 27 divided by 2 is going to be 13, I think. So we would look at this guy. And then I need another color. I'm going to go blue. So we'd now be looking at these two. And then 29 divided by 2 is going to be 14. So we'd have to look at this one. And then we would end up looking at 15 also. So in this case, we were able to skip indices 8, 9, 10, and 12. So depending on the exact situation, right, this algorithm is going to perform better or different. I think this would probably be like the worst case. And as you can see, in this situation, it does better than that linear search approach, especially as it gets bigger. That having of the search space is going to have a much larger like compounding benefit than it does in kind of a small example like this. All right, now that we have made it through this part, let's go do some coding. All right, so here I've just got the skeleton for our search range function. It accepts as the first parameter a slice of type int called nums, and then our second parameter is that target number we're looking for of type int, and then our return type, which is going to be a slice of int, which is just going to have two values. The first value, the 0th indice, is going to be that start index, and the second indice will be the end index. If we're unable to find the target within the slice nums, we just return -1, -1. So I'm just going to put our base case here, which is going to be if the length of nums equals 0, we're just going to return our slice of type int with the values -1, -1. And that's just because obviously if there's no elements in nums, there's nothing for us to search across to find the target. And then next, before implementing anything, I'm just going to kind of write what the idea here is. And it's going to slightly different from what I drew out on the iPad. On the iPad, right, we first did binary search to just find the target number. And then from there, we did binary search again to find the start index. And then we did it again to find the end index. So basically, we performed 3 different iterations of binary search. In the actual code implementation here, I'm just going to do 2. And the first one will be just to keep going until we find the leftmost index. And then we'll do it again, starting fresh, and perform binary search to find the last end index of it. So I'm just going to write out perform binary search to find first index of target in nums. And then I'll write again, perform binary search to find last index of target in nums. And then what we'll return is just going to be basically that leftmost and rightmost index. So it's going to be left, right. And now, as you can see, since we're going to be calling binary search twice, we'll just go ahead and implement that as its own separate function that we'll call from within this one. So I'm going to declare my new function up here. I'll just call it, oh my God, you scared me so much.
You usually hear me talking.
I have headphones on, man. All right, so I'm just going to declare my function up here for performing the binary search. And we'll just call it function binary search. And our parameters will accept the int slice nums and our target int. And then we're going to accept a third parameter, which is just going to be to tell us, are we looking for the leftmost or the rightmost index within num. So we'll just call it is left, and that'll be of type bool. And then we will return the integer, which is going to be, right, if it's left, if is left is true, that's going to be the leftmost index. And if it's false, it's going to be the rightmost. And if we don't find it, it's just going to return -1. All right, so now in the body of our function, we're going to initialize our left and right pointers for iterating and having the search space as we try to find the target number we're looking for. So we're going to have L, r is equal to 0, and then the length of nums minus 1. And then I'm going to add a third variable, which is going to be to keep track of the last place that we found the target at, right? Because first, we're going to perform binary search until we find the target. That might not necessarily be the actual start or end index that we're looking for. So we're going to keep track of, if we did find it, where was it? And then keep performing binary search until we don't find it again. And that's going to be how we know wherever that start or end index is, because we'll have kept track. And once we don't find it, whatever's in this new variable will be the last place we did find it at. So I'm just going to call it boundary. Typo. Boundary. And we're going to initialize it to -1 because we're just going to, right, kind of the case if we don't find it is -1. So that's where we start at. We haven't found it yet. And then we'll iterate for as long as L is less than R, right? If right ever ends up moving to a point where it's before left, then we didn't find it in the array. All right, so now within our for loop, the first thing we're going to do is find what is the midpoint between left and right. So we'll just do M is equal to L plus R divided by 2. And then our value, we're going to call it V, is just equal to nums at that index M. And now we're just going to check, did we find our target? So if the value is equal to the target we're looking for, well, in that case, we can go ahead and update our boundary because we know that we found the target at a position. So we're no longer going to return -1. And then if we're looking for the leftmost, right? So if is left, we're not done. We're going to keep binary searching until we don't find the target anymore. And that way we know that we found the start position. So what we're going to do now is we will move our right pointer over to M -1. And this way we're going to now start searching that left half of the search space and keep narrowing that down until we find the end or the start boundary case. And then otherwise, we're going to move our left pointer over to M +1. Whoops. All right, so now that was assuming that we did find the target. We update our boundary, and then we move our left or right pointer based on if we're searching for the start or end index. But if we didn't find our target, well, we'll just keep performing the binary search as normal. So if the value that we found is less than our target, that means we need to search the right half of the search space. So we're going to move left over to M +1. Whoops, I just called it L instead of left. And then otherwise, that means our value is greater than target, and that means we're going to move our right pointer over to M -1 so that we're searching the lower half of that search space. And then at the end here, we're just going to return whatever that boundary we found is. So if we never found the target, boundary is still going to be -1. So that's going to give us, right, that it's not in, our target number isn't in our slice nums. But anytime if we did find it, we updated boundary to be what that position is. And then if we're searching for the leftmost, we're moving our right pointer over to point 1 before that last occurrence of the target to search the lower half of the subspace and just keep doing that until we find that leftmost edge. Otherwise, if we were looking for the right, we move our left pointer over one to the right of where we found our target and keep searching the topmost part of the search space. All right, so now that we have this binary search function, we can go back down to our search range function, and we have this comment where we know we're going to perform binary search to find the first index of target in nums. So now what I'm going to go ahead and do is we're just going to have our leftmost edge is going to be equal to calling our binary search function. We'll pass in our int slice nums, our target, and then true, because again, we have this is left parameter for determining are we trying to find the leftmost or the rightmost edge, and so it's going to be true in this case. And then R is just going to be equal to performing the binary search on passing in nums, target, and then this time we'll pass in false. And then our return value is just going to be L, comma R, right? Whoops, wrong syntax. It's going to be our int slice with first index L, and the second index 1, is going to be right. And so if we never found it right, L will be -1. Otherwise, it'll be that first index of our target. And then same thing for right. If we didn't find it, it'll be -1. Otherwise, it will be that end index. Now, there's a couple little optimizations we can make to make this even a little bit better. So for instance, if we perform binary search to find our leftmost index, well, if that returned -1, that means that the target wasn't in there, right? Because it would have found it at some place, no matter where it was. Even if it was only once, left should have found it. So we can actually skip doing the second binary search if we didn't find it, because that means target was just never in the slice. We never could find it. So we'll do if L equals -1, we can just go ahead and abort right here. So we'll just return our int slice with -1 and -1. Now there's one more little optimization we can make to make this even a little bit better. So if you look at it, right, we're performing binary search for the leftmost index, right? And so it's going to start with L at 0 right at the end of the slice. And then we do it again to find our rightmost. And again, it starts with our left pointer at 0 and our right pointer at the end of the slice. However, since we already found the leftmost index of our target in the slice, we actually don't need to start with our left pointer at 0, right? We already know there's an occurrence of the target at the index pointed to by L. So instead of, when we're looking for our end index, instead of starting with L at 0 and R at the end, we could actually just start with the left pointer pointing at wherever we found it when we were searching for the leftmost index. And that way the search space will already be cut down, hopefully significantly. So what I'm going to do is in our binary search function, instead of initializing L and R at the same time here, I'm just going to get rid of L, the initialization of L there, and we're just going to initialize R, and we're going to actually take L as a parameter. And then what I'll do is I'll come down here, and when we're doing our initial binary search to find the leftmost index, I'll just pass in 0, because for this case, we do need to consider the entire slice. But then when we're searching for our rightmost index, we can just go ahead and pass in L, and that way we can skip over the entire search space that was already covered from our initial call to binary search. All right, now I've got this test file now to test our algorithm. It just has a bunch of different cases to make sure that we implemented everything correctly. So I'm just going to go ahead and run that now. And looks like we failed. So if we look at this, let's see, where did I go wrong? Okay, so in this for loop here, I made the condition for it to iterate as long as left is less than R. That should be actually equal, as long as left is less than or equal to R, right? Because once we get to one element, L and R are going to point to the same thing, and that's a valid case. We should check that, and our midpoint is going to be the whatever they're both pointing to in that case. So yeah, that was just a little mess up. We should keep going as long as L is less than or equal to R. So let me try running this again now. And sweet, it passed. Now there's one more thing that we can do to just make this even slightly more robust. And that's when we're calculating our midpoint between our left and right pointers, we did it as L plus R over 2. One kind of edge case we could have here is, right, left and right, they could both be the maximum value that an integer can hold. And so then when we add L and R, we're actually going to get an integer overflow, and that's going to mess everything up. So how we can actually calculate this without running into that is we could do it's equal to L plus R minus L divided by 2. And so this way, since we're subtracting L from R first, and then dividing that by 2, this gives us the exact same value, but just because we're subtracting L first, it's going to prevent having that integer overflow. And now let's run our tests again. And sweet, it passed. And there you go. That is our solution to finding the first and last positions of a target number in a sorted array written in Go.
BDSM. I mean ASMR.